Okay, hi apes. Mr. Block, it's Friday. I'm on my way to Omaha, and you guys are stuck here in the classroom. So sorry about that. Just wanted to do this video so that if you guys are still in your, I just finished the test mode, that you could just sit here and listen to me download this presentation. But you'll see that I'm skipping all the videos, and so every now and then I'll tell you maybe you should go here, maybe you should go here once you're done, because I don't think this one's going to last very long. All right, so as I told you on Wednesday, Thursday, one of the things that amazes me about this entire unit is that I was never a big sky person or big star person or anything like that. But after teaching it for 3 or 4 years, there's a lot of things that you should just get out of studying the stars and the universe, and that is the wonder of it all. There's just so many connections and so many unique situations and so many things that we've figured out and so many things that we still haven't figured out. But this picture I love just because right down the diagonal from left to right is the Milky Way. And if you ever get a chance to go somewhere where there's not as much light, you will see this sky. And that's the one thing that, you go outside your door right now and you might see, a star here, a star there. But you go up where there's not any light pollution and you'll see this particular sky. And right down that side is the Milky Way where we're at. And everything else outside of the Milky Way is something much further away and much more complicated. And then if you get a chance, you'll step outside and then that diagonal will look one way, and then you come out 2 more hours later, and you'll get to see that the Earth has rotated and that the Milky Way is now in a much different orientation. So that's pretty cool. So anyways, just if you get a chance, because that in that video that a lot of you guys didn't watch, one of the things that I heard is that 80% of all American kids will never see the Milky Way. And that's the one thing that's sad, because if you ever get to see something and get to feel what it's like to be that tiny, you share that experience with other people. But now you guys don't get to see that because 80% of us live in a place where there's so much light at night that we don't see it. All right, let's go through this set real quick. First of all, on Monday, we're going to try to get your textbooks returned. So please, please, please see if you can remember to bring those on Monday. If you bring them early, stack them into one of the pods or stack them on top of one of the pods today on Friday, and we'll just check them back in because you guys got the numbers. Remember, we checked them out by number. All right, we're going to be doing astronomy, and that's going to be Unit 10. There'll be a test. It will be the same as any of the other tests, and I can just tell you right now that this is a unit that we're teaching to the non-AP classes, so hopefully it will be an exam that you guys can use to pad your grade a little bit. All right, so the first thing is, what connections do you have with the sun? And we're hopeful that you can see that there's not just things that are cool and things that we run outside and things that people say, hey, go outside and look at. There's a lot of things that we can explain. So on the left, we have the northern lights, or the aurora borealis. And we're going to find out that that is actually the solar wind, and the solar wind that's being thrust at the Earth. And if the Earth didn't have its magnetic field, this solar wind would have prevented life on Earth. And so it's just one of the many connections where you say, well, how did the Earth form, and how did it get a magnetic core, and then therefore how did it get a magnetic field around it that allows for compasses to work, but more importantly, allows for that solar wind to split, some up to the north, some up down to the south. And so we're seeing that solar wind coming by the northern poles and being lit up here on the left. And then we've got the eclipse, and if you guys remember just a year or two ago, the eclipse, while pretty neat and very predictable, allows us to study the sun in a different way, because the middle part, that's part that we're going to be studying today, is covered up and we can see the outside. All right. So here is a picture. Now, if you get a chance, I'm not going to play this video, but this is a picture of the outer layers of the sun, and this is what we call a solar prominence. And then why we call it a solar prominence is because it is being ejected off the sun, and you can see how big it is compared to the size of the Earth. But then the sun's gravity is actually pulling it back in. So there's this large, uncontrolled explosion that's pushing that flame out from the left, and then it's being pulled back down by the sun's gravity. And that's, first of all, the more important thing for us to learn is that the sun is really just a massive explosion that's being held together by a massive amount of gravity. And therefore, it's got this great equilibrium that allows it to work. And we'll talk about that in a second. But this is a solar prominence, and if you get a chance, I'm gonna speed through this video, but if you get a chance, go back into these and watch this because it's a pretty neat little video. All right. All right. Another thing for you to look at, this is scale of the universe. So if you can, after this video, go to this website. It's linked right there on the top, and it'll give you an idea of just how big and how little you are. So try this scale of the universe website after we're done. All right, here are the suns. So this is for your notes. So make sure you have some notes out there. This is the first picture of, I think, 3 of the sun. And the sun has a core. And so in the middle of that core, that's where all the energy is coming from. We'll figure out how that is. And then there's some space. That space called the radiant zone. So we've got the core right here, and then the radiant zone right here. And we've got what is surely some convection currents going on right here. So the convective zone, bringing the hot out and the cool back in. And then we've got this green layer, the photosphere, the blue layer, the chromosphere, and then the corona, which is the flares around it. And those are the parts of the sun. And whether or not you remember them and where they are at, I think the main thing is that we need to know that there's this core. And then the corona is something that we never see unless there is an eclipse. All right, and so here is how we study the corona, because when we have an eclipse, that's when the scientists all pull out their cameras and they're trying to figure out, what's coming off the sun, and that's the only time that we're able to actually take a picture. Well, later on, we'll figure out exactly how they know all the things that I'm going to teach you right now. But one of the things I think that you should all make sure you understand is that there's never a ability of the scientists to actually land on the sun, grab a scoop of it, and then figure out what is happening. We had to figure it out a different way. And so you're going to figure out that we found out how the sun works and how, or what it's made of, through a much more ingenious way. And it's another example of how the human brain can figure things out. All right, here's another picture of that sun in a kind of like a pie shape with the core and the radiant zone and the convective zone, and then the outer layer, the photosphere and the chromosphere and the corona. All right, here's a solar flare. It's different than a solar prominence in that a solar flare is actually so large that it actually escapes the gravity of the sun. And so you can see this one being pushed out, but doesn't have the ability to be able to be pulled back in because it was such a large explosion off the surface of the sun that it couldn't be pulled back by the sun's gravity. All right, and then we've got this one right here, the solar prominence that's being pulled back in. All right, this is the sun over the 6-period day, and you can just see that there's just a lot more going on than we see with the naked eye, when it's just something that we can't really look at because it's unsafe to look at. So this is a great picture of 6 days of the sun. You can see that it's rotating like the Earth, and it's got lots going on the surface. All right, the dark parts, these are called sunspots. So you'll need to know those sunspots. These are cooler areas of the sun's surface, and they actually come in pairs. And so you can see them coming in pairs, and one is a north magnetic pole and one is a south magnetic pole. And what we've noticed about sunspots is that they are very predictable. Not necessarily the amount, but the way that they ebb and they flow. And so here is a graph of sunspot activity over the last 200-300 years. And you can see it's on this 11-year path. It spikes and then it comes down, and it spikes and it comes down. And there's no it's always going to hit the same number on the top. But it is a a pattern that is very predictable from the standpoint of when's it going to go up, when's it going to go down, right? And so it's very predictable. There's another sunspot prediction versus actual. And so this is a very studied thing. There's a lot of ideas whether or not sunspot activity is connected with global warming, and the reality is that we've never been able to find a connection between the two. All right, so how does the sun work? How is it so hot, and how is it providing us so much energy? And this is something that you need to know. It's called nuclear fusion, and fusion is different than fission. Fission is when an atom breaks apart into little pieces. Fusion, to fuse something, is to put it together. And so you need to know this, and we're going to go through it real quickly, but then I'll show you what I expect you to remember from this next 5 slides here, okay? So nuclear fusion. What is nuclear fusion? Well, nuclear fusion, you need to know what the atom is made of. And so an atom's got a proton and a neutron in the nucleus with electrons outside. And I'm very hopeful that you guys know this, because I actually have to spend some time with our other 9th graders saying, okay, remember this, and they look at me like, I've never heard of anything like what the atom looks like. And so I'm hopeful that you guys do know what the atom looks like, and that there's protons and neutrons. The protons are the things that define whether or not something's an element. So 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium, and just keeps going from there. And so this is the atom. And so what's happening in the sun is we've got hydrogen. There's just a ton of hydrogen across the whole universe. Hydrogen is everywhere. And hydrogen is just 1 proton. There's no neutrons. It's got an electron. It's got a mass of 1. So we go, here's the protons, the atomic number. You'll learn this in chemistry, is down here. The mass number, which is the combination of protons and neutrons, is right here. And so hydrogen is the most elementary atom or element in our universe, right? And so hydrogen starts out and just sitting there, and it starts to come together. And so here's our sun. Our sun is what we call a main sequence star. Main sequence stars are not dying and they're not dead. They're normally just plugging along. And so in the main sequence star, there's this thing called hydrostatic equilibrium. That is basically this is trying to explode outward while the gravity is pulling it back in. And it's this equilibrium that allows for our sun to work very well. Got 2 minutes left, so we're going to keep going real fast. So there are steps in fusion. 2 hydrogen atoms come together, and they become this heavy hydrogen. Okay, so it's got an extra neutron in it called deuterium. That deuterium sits next to another hydrogen atom, and it becomes helium. So they fuse together, and they become helium. Then 2 helium atoms project off a proton, and then they combine to become the helium that we all know. And so this is a big step. And then it creates what's called the alpha particle, and the alpha particle is the thing that builds everything else. So what do you need to know? Because that's a lot, right? Here's the total process of hydrogen burning or fusion right here. And every time you see something come together, it gives off energy. So you can see 1, 2, 3, 4, 5 different types from making 2 hydrogen atoms into helium. What do you need to know? You need to know this. 2 hydrogen atoms come together, a bunch of stuff is happening, and it becomes helium. If you walk out of this class knowing that, then you are a successful person in the class, because now you know that fusion is 2 hydrogen atoms becoming helium. And then later on, we'll find out that the sun actually takes helium and fuses it together to make the next couple elements. All right, how old is the sun? About 4.6 billion years old. We know that it's got 75% hydrogen and 25% helium, meaning that it's still got a significant amount of hydrogen to burn, and therefore will continue to live for a long time. All right, and so this is the fusion that creates the energy. We've got about 30 seconds left in this video before it goes dead. So I'll just wish you guys a great weekend. I know it's going to be cold and rainy, but at least relax, get some sleep, and I will see you on Monday with your Chromebooks. Talk to you soon. Bye-bye.